Hi, welcome to A-Level Stats, Year 1, Chapter 5 Probability. This is the third of the three really super quick chapters, which basically all follow on from stuff you've kind of seen at GCSE, maybe with the odd new thing included. Let's dive in. We have some definitions here to remember. So often in stats like a 1-mark question, I'll ask you to define this thing. So we have 4 things there: experiment and outcomes, event and sample space. Okay, I'll let you read those, they're fairly straightforward. With probability, occasionally we need to interpolate. So here we've got this question, which I think we saw earlier in chapter 2, where we had height and frequency, with a probability that someone at random has a height under 165. So we have 34 people, so we something out of 34, under 165, we're going to have all of these, and then exactly half of these. So it'll be 4 plus 6 plus 4. So again, interpolation can crop up in quite a few different chapters. Next, you have Venn diagrams. Okay, these were like the mainstay of GCSE and came up quite a lot. Let's just go for one of the really basic idea. So we have 100 people. We have 3 options: run, swim, and cycle. So that will correspond to 3 different circles. With Venn diagrams, you always want to start from the middle. Okay, so 25 do all 3. Let me change colour for that. So we've done that one. 35 run and cycle. So 35 run and cycle. We've already got 25 in there, so we just need another 10 to give us a total of 35. In case of this, you basically always want to subtract from the stuff more in the middle. Moving on, a total of 30 people swim and cycle. We've already got 25, so we just need another 5 in there. 40 run and swim. We've already got 25, so we need another 15. 60 cycle. So far in my cycle bubble, which is this one over here, I have 10, 35, 40 people. So I need another 20 to give us my 60. 48 swim. So far this many swim, which is 45. So we need another 3. We are told 65 run. So far I've got 50 who run. So I need another 15 here. It's also possible that some people don't do any of those options. So draw the box. Any who don't do any of those options, we're going to write on the outside here. We know there are a total of 100 people right at the start. So if we add up all these numbers and then take it away from 100, we can work it out. If you add all these together, that comes at 93, I believe. So there's 7 people who don't do any of those 3 forms of exercise. Okay, another problem like a Venn diagram, especially at A levels, is where they don't give you numbers, they just give you probabilities. So here we've got 3 events called A, B, and C, and we have 2 missing values to work out. We're actually given some information. We're told that the probability of B is the same as the probability of C. And we can use that to work out A. If we add everything together in C, so probability of C is going to be these 3 things added together, which comes out at 0.48. That must equal the probability of B. Where if we add together all these things, we have 0.47. 0.57 plus A. So this question I've slightly messed up because A is going to be negative, but you get the gist. If I just cheat and say this is 0.07, then we're back on track. So here A would be 0.01. Then we can work out B. I'm not going to. You can work out B because you know that all the probabilities in this entire Venn diagram must add up to 1. So you add up everything you've got so far, and then take it away from 1, and you'll be left with the probability of B. We have a few definitions and notation to go through now, I'm afraid. So, some definitions. If 2 things are mutually exclusive, that means they cannot happen together. So the best example I can think of is rolling a 3 and a 4 on a die. The odds of so you can't roll a 3 and a 4, and if you want to work out the odds of rolling a 3 or a 4, you just add together the odds of getting a 3 and a 4, if that makes sense. Independent mean that 2 things do not affect one another. Okay, so the odds of probability A will not affect probability B. A good example is rolling a dice or a die and flipping a coin. So whatever the dice roll gives you won't affect your coin flip. They're independent, they do not affect one another. Okay? We have a definition for independence which we often use. And if two things are independent, we have this fact, which is basically stating the probability of A and B equals probability of A times the probability of B. Speaking of that, let's go through this notation. So here, P stands for probability. So PA will be the probability of A, which will be everything in this circle. So I've got 6 things and a total of 25. So that'll be 6 out of 25. Probability of A dash, this little dash just means not A. So it's going to be everything that's not in my A circle, which is the 10 and the 9. So it'll be 19 out of 25. This little U stands for union, and it basically means the probability of A or B. So A or B is any of these 3 numbers. So add them all together, we have 15 numbers here out of a total of 25. This little N symbol means intersection, and basically it stands for A and B. The odds against something that's in A and B, I've only got one thing there out of 25. And you can merge these together in quite interesting ways. So here's a probability of something being in A and not being in B. And you work it out, that only gives us these numbers, or this single number. That's the only number that's in A and it's not in B. So that would be 5 out of 25. We then have this one, which is the probability that it's not in A and it's not in B. So it's not in either A or B, which basically means I'm outside the circle. So it will be 10 out of 25. Last one. This little line basically stands for given that. So it's basically the probability of A given that B has already happened. So it's basically saying we know we're somewhere in the circle of B-ness. So I'm basically one of these 10 values. If I'm in that circle, what's probability that A is also occurring? In this case, it will be 1 out of 10. I have one value that's in A, and I have 10 values altogether. Okay, hope that was just recap from GCSE stuff. You also have stuff from the formula booklet. Most of this is used more in year 2. I would say right now in year 1 stats, you kind of care about this one. And for independent events I mentioned earlier, you have this test here. Okay, the other ones will use more often in year 2. Okay, I've got some example questions to go through. So we're going to some probabilities. We're going to look at the probability of A or B. For that, we can just use this formula here. Probability of A or B, again there's a missing P here, is going to be the probability of A plus the probability of B minus the probability of A and B. So working that out, if you add these two together, it gives you 0.8, and then we minus 0.13, so it's going to be 0.67. Next for part B, we're going to work out probability that we're not in A, given that we're not in B. For this, I don't know the best way to do it. In my head, what seems easiest to me is just do a quick Venn diagram, and then we can sort of put the probabilities in the right place. So I've got A and B. I know the overlap is 0.13. For these odds, I now need to take away that 0.13. So I'm going to have 0.22 and 0.32. Probabilities must add up to 1. So if I add together these fellows, I get 0.67, which means that being outside is going to be 0.33. So on to this question. I want to work out the probability that I'm not in A, given that I'm not in B. So let's highlight not in B. Everything not in B is everything outside that circle, which basically just includes these two numbers. From those, I can work out the probability that I'm not in A. I've only got one number that's not in A, so it's going to be 0.33 out of all the numbers that weren't in B. which was 0.33 and 0.22, which adds together to 0.55. And that will actually simplify down to 0.6. Okay, let's keep going. The event C, we have a new event, has probability of being 0.2. We are told the events A and C are mutually exclusive, and the events B and C are independent. So, in part D, we're drawing a Venn diagram anyway. I'm going to start drawing it now, just to get a handle of what's going on. So a key thing with mutually exclusive events is they cannot both happen. Think back again to rolling a 3 and a 4 on a dice. You can have them both at the same time. So if events A and C are mutually exclusive, that means they have no overlap. Their Venn diagrams should not touch. So it's going to look something like that for A, B and C. I can fill in some of these. I know this is 0.22 and this is 0.13. But I'm not sure what's going to go here, here and here. Okay, we can work that out by using the fact that events B and C are independent. So again, our test for independence, and you are given this, that states the probability of B and C is the probability of B times the probability of C. And these two things on the right we do know. Probability of B, we're told, is 0.45. Probability of C, we're told, is 0.2. And if we times those together, that will give us the probability of A and B, which is 0.09. We can now do part D. We can draw a Venn diagram. 0.09 goes here. We know probability of C was 0.2, so this will be 0.11. Probability of B is 0.45. I've got 0.22 here so far, which means I'm going to need 0.23. So that all these things add together to give me 0.45. Also to fill out what's going to go over here, and that is going to be 0.22. Again, just by adding up all these things and taking it away from 1. Okay, last question, and again they're really messing us with the awkward notation. So we're going to work out now, find the probability of not B or C. Okay, let's highlight that on my Venn diagram. So B or C is all this stuff over here. I want not that. So I want everything that's not in B or C, which would be everything outside those two circles, which is just these two numbers. Add them together, and we are done. Okay, so these questions can get fairly messy. The key thing that we're going to test you on is, do you know and can you use the fact that things are mutually exclusive and independent? So make sure that part of this video made sense to you. Okay, a few more examples to go through, I'm afraid. This question again is super common. So Venn diagram has 3 events A, B and C. And we have the probability associated in the region. Okay, and we then have constants P, Q and R to work out. And we are told that A and B are independent. So we've got an independence test. That is probability of A and B will equal PA times PB. Okay, probability of A and B is 0.1. Probability of A is going to be P plus 0.1. Again, don't forget to add this thing back into it. Times by probability of B, which is 0.4 from adding these 3 numbers together. That means I can now work this out. P plus 0.1 will now equal 0.1 over 0.4. On your calculator, that gives you 0.25 because it's the same as a quarter. So from here we can see that P is going to be 0.15. And let us add that in. Probability of P is 0.15. We are then told the probability of P given that C is 5/11. And I'm going to stop there. So if we go any further, I'm sort of treading into year 2 stats, which I don't want to do right now. Okay, I hope this is the last thing, so I think it is. This is tree diagrams. And this again you've seen from GCSE. Not much has really changed, to be honest. So let's go through this one example super fast. We have 6 coins in a bag. Laura takes a coin. Famida takes a coin. We're going to work out the probability that Famida's coin has a greater value than Laura's coin. So Laura gets first pick. Let's do a tree diagram for Laura. She has 3 options. Well, she has 6 options, but they relate to 3 unique coins. So she can either get a £2 coin, a £1 coin, or a 50p coin. And we can work out each of those odds based upon how many coins of that type are in the bag. For Famida's pick, I'm going to try and be slightly clever, as dangerous as it is. I don't really care what coin Famida gets. All I care about is if it's higher or lower. So for each one, I have 2 branches for higher, and then H dash, which means not higher. Okay, I could also use NH, but I'll stick with this for the time being. So, if Laura picks the higher coin, so if Laura picks a £2 coin, it is then impossible for Famida to pick a coin higher than £2. If Laura picks a £1 coin, so say this one, that coin is now gone, Famida can only pick the greater coin if she gets the one remaining £2 coin. And because Laura's picked a coin, there are only 5 coins left, so it's 1 out of 5, which therefore means this is 4 out of 5. Same for the 50p. 50p is gone, so there's only 5 coins left. Of those 5 coins, 3 of them have a greater value. So it's now 3 out of 5 and 2 out of 5. I want to work out the overall probability that Famida's coin has a greater value than Laura's coin. That is going to be these 3 branches, even though one of them has a probability of 0. So that one just equals 0. If you go along branches of a tree diagram, you must always times. So this is 2 6 times 1/5, which is going to be 2/30. This is 3 6 times 3/5, which is going to be 9/30. Now I've got all these separate options that Famida can get a coin with a greater value. To combine those, we just add these 3 probabilities together. So the overall probability is going to be 11 out of 30. Okay, yeah, I'm not doing that. Okay, what I will do is this question, because it gets more to see like in A-levels. So, another tree diagram we can see is about someone being late for work on 2 days next week. We're then told something slightly interesting here. We are told that Bismarck was late on a Tuesday. That means we know we're either down this branch or down this branch. So the only 2 branches where he's late on a Tuesday. We want to work out the probability that he was also late on a Monday. Okay? To do this, let's work all these things out. So working out he's late on both days, we do 0.07 times 0.02, which gives us this. We then do the same here, so 0.93 times 0.11, which gives us that number there. To work out the probability he was late on a Monday, we're going to take the probability of him being late on that day, and we're going to divide it by the total probability of him also being late on a Tuesday. Okay, so because we already know that he was late on a Tuesday, we know we're down one of these branches, so we have to divide the probability of already being down that branch. And to do that, we just add these 2 numbers together. Okay, this is the exact thing we have with the Venn diagrams when we were doing probability of A given that B. Okay, it's the exact same idea. Okay, that's all kind of the new stuff we need to know for probability. I hope that was useful, and thanks for listening.